This is a quote by a physicist as a comment on one of his experimental results. He said about his experiment, it was as if you fired a 15-inch shell at a piece of tissue paper, and it came back and hit you. So let's talk about his experiment and what he was doing. Rutherford at the time had been doing a lot of research on radioactivity. He was friends with Marie Curie and her husband, Pierre, and he had done a lot of studies looking at the different kinds of reactivity, and more specifically, he was curious at this time about alpha particles, which are, at the time he didn't know what they were, but we now know that they are helium 2+ nuclei. So that means we have 2 protons in the nucleus, since it's helium, and it also has 2 neutrons. And it doesn't have any electrons, and thus it has a 2+ charge. So what Rutherford did, he took a piece of radium and he put it inside a lead box. And the lead box had a small hole in it on one side so that the radioactive alpha particles could come out of that hole in the direction that he wanted. And then he shot the alpha particles at a piece of gold foil, a very thin piece of gold foil. And he was curious to see if he could learn a little bit about the structure of the atom using this experiment. So if we look back at our quote, we would say that our alpha particles here, the alpha particles are the bullets that are coming out of our alpha particle gun, and gold foil is our tissue paper. And we have these pretty fast and massive alpha particles that we're shooting at it. But why was Rutherford expecting that to happen here? It's not necessarily straightforward, at least to me, why you would think these alpha particles would just go straight through the gold foil. So what Rutherford at the time was doing was he was testing the plum pudding model. So this is pretty early in history where we being scientists way back then, knew that J.J. Thomson, another physicist, had just discovered electrons. So we knew the atom had these particles in it that were small, that were really small. We knew that they were less than 1% the mass of a hydrogen atom, so way smaller than an atom. And we knew they were negatively charged. So I'm going to call them electrons, because we know they're electrons now. And so J.J. Thomson knew that electrons existed based on his experimental results, and he proposed, based on his results, that an atom looks something like a plum pudding. And if you don't know what a plum pudding is, because maybe you're not British or you just don't like dessert, you can also imagine it looking something like a chocolate chip cookie. So we have these little negatively charged particles that are stuck inside the atom, but most of the atom is made up of a positively charged soup. And this was mainly because the atom overall has to be neutral. Scientists knew that atoms were neutral, so there had to be something there to cancel out the negative charge of the electron. So because Rutherford was starting with this in his mind for what the gold atoms look like, he could actually do mathematical predictions on what the alpha particles would do. And what he predicted was that they would just go straight through. You can use physics equations to look at the electric field that's generated by this positively charged soup, and it turns out that the field, because the charge is spread out all over the atom, the field is very weak. And so what he thought would happen was that all the particles would just go straight through, and then occasionally one of them might be bent a little bit, since we do have a positively charged soupy atom. Depending on where the alpha particles goes through, he thought you might see a little bit of deflection, but mostly they should go straight through. And I guess we started with a spoiler, because we know that, well, he didn't quite get what he expected. So what exactly did Rutherford see? Well, he shot his alpha particles at his tissue paper, and he saw most of the particles go straight through, just as he expected. In fact, he saw almost all the particles go straight through. He saw a couple of them be deflected a little bit, so they got deflected off their path maybe about 1 degree, so barely enough to be able to see it. And, if he had not been a curious chemist, we would maybe still think right now that this is what an atom looks like. But luckily, Rutherford was a very thorough chemist, and he also thought it might be interesting to detect whether particles came not just here. He didn't just put a detector screen here. He put a detector screen that went all the way around. So all the way around, almost all the way around, giving enough space for the alpha particles to go in. And he was being really careful here, because he really didn't expect to see anything right around here or here or here, or really anywhere except for here. But it turned out that for every 1 in 20,000 alpha particles, or some crazy tiny number like that, for every 1 in 20,000 alpha particles, he saw the particles hit the gold foil and bounce back. And that's crazy, right? That's exactly what you don't expect when you hit a piece of tissue paper with a bullet. So the first thing he did, I think, was not go, this is really crazy. We just won a Nobel Prize here. I'm pretty sure the first thing he did was, this is weird. And then he probably checked his experimental results, and he tried to repeat it, and he checked everything to make sure nothing was going wrong. And it turned out that, yes, something was actually happening. This 1 in 20,000 alpha particles was real. So what did this mean? This meant that we needed a new atomic model. We had to explain somehow that a tiny fraction of the alpha particles was getting bounced back. So how did he do this? He knew there was something in the atom that was tiny, massive, and positively charged. And he knew that had to be tiny because not very many alpha particles interacted with it, because most of them went straight through. He knew that had to be massive and positively charged because, well, the electrons are really small, and most of the particles went straight through. So whatever these particles were interacting with had to be very small, but really heavy, which is how they bounced right back. So he made a new model of the atom that incorporated these requirements. And what he said was that there must be something in there with these properties, which we now call the nucleus. And it's really tiny. In fact, he was able to calculate not exactly. He was able to calculate approximately how big it was based on how many alpha particles hit it. And he said it was approximately 1/10,000th of the volume of the atom. And then what else do we have? We know we have this nucleus, which is positively charged and tiny and massive. And then we also have our electrons. And then what's the rest of the atom doing? Based on all of this, that means most of the atom is actually empty space. Since the electrons are really small and the nucleus only takes up 1/10,000th of the radius, the rest of that space is all just nothing, which is kind of crazy. So based on this particular model that Rutherford made next, he was able to explain his results. He was able to explain that most of the alpha particles just went straight through, and then every now and then an alpha particle would come really close to the nucleus, and then that would get deflected a little bit. And even more rare, an alpha particle may hit a nucleus straight on, and then it would get bounced off because the nucleus is super heavy and because it's positively charged. So it would repel the positively charged alpha particle. Rutherford called this particular model, or we call it now, I'm not sure which actually, he called it the nuclear model. This actually looks pretty similar to the modern picture of the atom that most people think of. There's a lot of questions that are still not answered here, like what exactly the electrons are doing, or where are they? Where are the electrons? But because Rutherford proposed this new model, other scientists were able to design new experiments to test it, and not very long afterward, we had a pretty good picture of what was going on the level of the atom.